Workerinis, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 28. We start by writing the number 1 in the center of a grid. Then we write the number 2 next to it, and continue incrementing our counter in a clockwise spiral. When we loop all the way around, we start a third layer, and so on. In the example from the problem description, we draw a 5x5 grid. Then we sum the numbers on the two diagonals to get 101. The problem asks us to sum the same diagonals for a 1001 by 1001 grid. Obviously, I won't be drawing a grid of that size, as I, believe it or not, have better things to do with my time. But we can easily have a computer draw the same grid. We're going to be working with two-dimensional arrays, so let's start out with an array-based language. Today, we'll do our drafts in Julia. To start with, we'll model the grid in the problem exactly the way it's described here. Our grid will be a two-dimensional array, or matrix in Julia terminology, and we'll write a point structure that we'll use to index into the matrix. Next, we'll define the plus operator on the point type. Like many modern languages, Julia lets programmers overload the behavior of built-in operators on custom types. In principle, we could also define subtraction, negation, and scalar multiplication, but we don't need all of that for this particular problem. Next, we'll define two getters. Similar to Python, there's no real concept of a private field on a structure in Julia. All fields on a structure are accessible to everyone. But unlike Python, idiomatic and well-written Julia code generally regards the fields on an object as an implementation detail. Since we want the x and y coordinates to be public, we'll define getters to access them. Next, we want to be able to index into a matrix with our point structure. The bracket subscript notation used to index into an array, or really any value, can also be overloaded in Julia. So we define getIndex and setIndexBang to work on our point structure. Note that by convention, methods in Julia which mutate a value in place are suffixed with a bang or exclamation mark. And setIndexBang is no exception. Also note that we need to import the names of the operators plus, getIndex, and setIndexBang from the base package. If we didn't do this, we would implicitly define new functions unrelated to those in base, which is not what we want here. Now let's make our spiral. We're going to have the cursor start in the middle of the grid facing right. He's going to place a number, then move in the direction he's facing. After that, he'll look to his immediate right. If he doesn't see a number there yet, he'll rotate to face that way. This pattern continues until we step outside the bounds of our desired array. Let's write that in Julia. First, we write a quick helper function to rotate a point clockwise by 90 degrees. Note that I haven't annotated the argument type of this function like I did with the others. Since I'm using the getters x and y, my rotate clockwise function will theoretically work on any object which responds to those two getters. Obviously, in the case of this particular Project Euler problem, that will always be an element of the point structure, but the principle of the matter is still relevant. Also note that we return a new point object. I haven't marked our point structure as mutable, and data in Julia is immutable by default. Having smallish data structures like point be immutable makes the code much more predictable. If a function takes a point as argument, I can be confident that function won't modify it, because nobody can. And if a function returns a point, I don't have to worry about whether my modifications will clobber some other part of the code base. I've lost count of the number of times I've worked with a third-party API, often in Java, with a mutable point or vector class. In those cases, whenever I get a point object from a method, I'm left wondering if I need to defensively copy it before doing anything. Making these small mathematical structures immutable eliminates that whole problem. Now for our function to produce the spiral itself. We take one argument, the desired width and therefore also height of our resulting spiral. First, we produce an array of all zeros. We'll start our cursor in the center of the array. In Julia, ordinary division done with the forward slash is always so-called true division, which produces a floating point value. Integer division can be done with the function called div, or equivalently with the division sign Unicode symbol. And you know how much we love Unicode operators on this channel. Our cursor starts out facing to the right and has a counter value of 1. Now we'll loop forever. Or rather, we'll think about our stopping condition in a minute. Inside the loop, set the array position to the current counter value, move the cursor, and increment the counter. Then, check if there's something to the cursor's right, relative to the direction he's facing right now. Or, more specifically, since we initialized our array to all zeros, check if the thing to our right is non-zero. If it's 0, rotate the cursor to the right. Now, when we attempt to set or get an array index that's out of bounds, Julia will throw a bounds error. So our stopping condition can simply be catching that error. Unlike in Python, but similar to JavaScript, Julia try-catch blocks are untyped. That is, we blindly catch all exceptions and then consider rethrowing the exception if we don't feel like we can handle it. Finally, at the end of the loop, return the array. Now we have a function to produce the array. Let's sum up the diagonals. This function is pretty simple, so I'll move quickly. Get the height of the argument array, then iterate from 1 up to the height, remembering that Julia arrays are 1-indexed, not 0-indexed. Add in the array index on the first diagonal, then, if we're not in the center of the array, add in the array index on the second diagonal. This extra check ensures we don't double count the value 1 at the center of our array. Finally, return the sum. Our main code is quite simple. Make a spiral, sum the diagonals, and print the result. This solves the problem instantaneously in Julia. Let's make a couple of small improvements. The bounds error exception was a nice trick to detect the end of iteration without doing any additional work, but it does feel a bit sloppy. So let's rewrite our loop to correctly track the end. First off, we'll preload the very first element at the center, since the center position is sort of a corner case. Then, we know the size of the resulting matrix is dim times dim, and a matrix with those dimensions has a total of dim squared elements. So we'll use a for loop that goes up to dim squared, and since we already placed our first element as a corner case, we'll start at 2. Inside the loop, do our check for a clockwise rotation first, then assign the current loop counter to the cursor's position, and move the cursor. That cleans up the loop quite a bit and simplifies our program. But we can go way further. Let's take another look at our spiral. We draw this whole spiral and store it in memory, but we really only need the diagonals. In this 7x7 example, the diagonals are 1, 3, 5, 7, 9, 13, 17, 21, 25, 31, 37, 43, and 49. Let's look at the relative differences in these values. The first two values are 1 and 3. 3 minus 1 is 2. 5 minus 3, similarly, is 2. 7 minus 5 is 2, and 9 minus 7 is 2. After that, when we go from 9 to 13, we have a jump of 4 instead of 2. Then 13 to 17 is another jump of 4, 4, and 4 again. Next, we jump by 6, then 6, then 6, and 6 a fourth time. I'm sure you can see the pattern from here. The difference increases by 2 for every 4 values. We don't need to store any large arrays. All we need is the most recent value and knowledge of what our current delta is. Let's rewrite our SumDiagonals function with this new knowledge. Instead of taking an array as argument, we'll simply take the desired width of our grid. Our sum starts at 0, our current value starts at 1, and our initial delta is 2. We also keep a counter for when we need to increment the delta value. We're going to loop until we exceed width squared. Inside the loop, add the current diagonal value to the sum. Increment the value, then count down our delta counter, and if it's just hit 0, increment delta by 2 permanently. Outside the loop, simply return the sum, and we're done. This is much simpler than what we had before, but believe it or not, we can actually go further. Let's regard the value 1 in the center of our grid as a special case once again, so we'll ignore it for now. Aside from that one special case, the upper right diagonal is very predictable. It's 9, 25, then 49. That's 3 squared, 5 squared, and then 7 squared. And the pattern continues with 9 squared, 11 squared, and so on if we were to keep drawing. The other 3 diagonals in a given square can be calculated relative to the upper right diagonal. The first square, again excluding the special case of the center value 1, consists of 3 squared and numbers 2, 4, and 6 below 3 squared. The next square consists of 5 squared and values 4, 8, and 12 below that. After that, we see 7 squared and values 6, 12, and 18 below that, and so on. So we don't even have to iterate by diagonals, we can iterate by squares instead. Let's write that in Julia real quick. Our sum starts at 1 since we're treating the center of the spiral as a special case. Our loop counter variable indicates what value we're going to square in order to get the upper right diagonal value, and our delta starts at 2. Loop as long as the counter is less than or equal to the desired width, since the final diagonal is equal to width squared. Inside the loop, add the 4 diagonal values. The upper right is simply loop counter squared, and the other 3 are relative to that value. The amount to subtract in order to get there is our delta variable. Next, increment the delta variable and the loop counter by 2 each. Finally, return the sum. And this is about as simple as it's going to get. If we really wanted to, we could write this out as a summation and try some algebraic simplifications to see if we can eliminate even that loop. But given that this program already runs instantaneously, I don't find that overly necessary today. It's time to talk about our language of the week. This week, we'll be using Befunge. We already talked about Befunge in the context of hexagony, but now it's time to use it for a real Project Euler challenge in its own right. Befunge is the oldest major two-dimensional esoteric programming language, and it's largely considered the father of that paradigm. As such, there are a lot of different versions and interpreters out there. Today, we'll work in Befunge as it was originally designed, the version commonly called Befunge 93 nowadays. Befunge is a two-dimensional programming language, sort of like hexagony, but a lot more like Labyrinth. We have an instruction pointer which starts at the top left corner and is initially facing right. The instruction pointer executes the instruction at its current position, then moves in the direction it's facing. Befunge is stack-based, so operations like addition and subtraction push and pop from a global value stack. The thing that makes Befunge unique is its data model beyond just the value stack. Many stack-based languages provide enough stack shuffling primitives that we can get effectively random access to our stack, thus turning the program's allegedly FIFO stack into an arbitrarily large array. Languages like that generally use the value stack as their whole data model. But Befunge doesn't have that. In fact, as you'll see in a minute, our stack shuffling primitives in Befunge are quite limited. Instead, Befunge allows us to store data directly in the code space. The lowercase g command pops 2 values off the stack, treating them as x and y coordinates. Then it gets the character at that position in our program's source code and pushes that character's Unicode value onto the stack. Conversely, the lowercase p command pops 3 values off the stack, y, x, and a new integer v, and stores the character with Unicode value v at the indicated source position in our program. This is how we modify Befunge programs, and it's how Befunge's data model works. In a purely stack-based language, we would use exclusively the value stack to store all of our values. But in Befunge, we're only going to use the stack for things we need immediate access to at the given moment, and then we'll store anything else as literal values in our program's source code. However, this does create another small problem. We can only store numerical values in our source code if they happen to be valid Unicode values. More specifically, the interpreter we'll be using today is written in JavaScript. JavaScript uses UTF-16, and the interpreter uses string.fromchar code to convert between numerical values and characters in our source code. That means in the interpreter we're using today, we can only store integers from 0 to 65,535 in the code. That means negative numbers, as well as numbers too large, can't be stored in our code. For those of you who have been following along at home, you'll have already realized that the final sum we get is on the order of magnitude of a few 100 million. So we can't store that sum in our program's source code at any point. The final total will have to stay on our value stack forever. Fortunately, all of our other variables are just fine. Loop counter starts at 3 and never exceeds 1003. Delta likewise starts at 2 and goes up by 2 at a time, with a final value of 1002. With that in mind, let's talk about Befunge's built-in commands. There aren't very many of them, and we've already discussed what are arguably the 2 most complicated ones. The integer digits from 0 to 9 each push the corresponding numerical value onto the stack. These do not compose with one another, so if we write 5 followed by another 5 in our code, that pushes 2 instances of the number 5 onto the stack, not the number 55. All of our basic arithmetic operations are available. Plus for addition, minus for subtraction, star for multiplication, and a / for division. Note that the only data type in Befunge is the integer, so division is always truncated. Amusingly, the Befunge 93 specification states that in the case of division by 0, the program should stop what it's doing and interactively ask the user what result they'd like. The interpreter we're using today doesn't obey that behavior, but it's amusing nonetheless. The % acts as a modulo operator, popping 2 values off the stack and pushing the remainder of integer division. Bang is logical negation. Since integers are the only data type in this language, logical negation takes 0 to 1 and all other numbers to 0. The backtick is the greater than operator. This is also, incidentally, the only comparison operator we have, so any comparisons will either need to be phrased as a greater than or as equality against 0. Then we have the 4 directional inputs. A greater than sign, less than sign, caret, or lowercase v will unconditionally force the instruction pointer to face in the direction of the arrow. There's also the question mark operator, which sets the instruction pointer to face in a random direction. I suppose this is useful if you're in a gambling mood. Underscore and vertical bar are the 2 if statements we have available to us. The underscore is the horizontal if statement. When the instruction pointer encounters the underscore, it pops a value off the stack. If that value is 0, we're forced to start moving right. But if that value is non-zero, we move left instead. This is an absolute direction, regardless of which way we were facing when we entered the instruction. Vertical bar works the same way, but vertically. In the case of a vertical bar, we pop 1 value off the stack and set the direction of the instruction pointer to down if the value is 0, or up if the value is non-zero. We also have a very limited supply of stack shuffling commands. Colon duplicates the top stack value. Backslash swaps the top 2 stack values, and $sign pops the top stack value and throws it away. That's it. That's the extent of our stack shuffling capability. Values more than 2 positions deep on the stack might as well be on the moon, since all we can do is swap the top 2 stack elements. For input and output, we have the usual 4 commands: output integer, output Unicode, input integer, and input Unicode. These are represented, respectively, as dot, comma, ampersand, and tilde. The output commands pop 1 value from the stack, and the input commands push 1 value to the stack. The hash command skips over the next character unconditionally, which can be useful if your program needs to overlap itself. We already discussed lowercase g and lowercase p, which get and put program source code characters, respectively. Finally, the @ terminates the program. There's one other command in Befunge which we won't need today but is interesting nonetheless. A quotation mark causes the Befunge interpreter to enter string mode. In string mode, rather than reading characters as commands, Befunge interprets every character as an instruction to push its own Unicode value onto the stack. This continues until it sees another quotation mark, which deactivates string mode. This can be useful if you're trying to output a specific string of text, but we don't need that today. With all of that out of the way, let's talk about how we're going to store our program. As we mentioned, the total sum is far too large to store in the program's source code, so that value will live at the bottom of our stack for the duration of our program. Aside from that, our variables will be stored in the first row of our source code. Specifically, at index 1, 0, we'll store the loop counter, at index 2, 0, we'll store the delta variable, and finally, at index 3, 0, we'll store the constant number 1003. That last one is merely a convenience, so we don't have to repeat the arithmetic to produce the constant number 1003, which is our loop's stopping condition at every iteration. Let's get started. The first thing we'll do is move down to the second row. It's not a huge deal, but it would bother me somewhat if we were overwriting program instructions to store variables, even if we never plan to visit those instructions again. So by moving down to the second row, we ensure that the 3 source code positions we plan to use for variables are unoccupied. Now, put the number 1 on the bottom of the stack. This is our total sum and we'll update it as we go. Next, put 3 in the loop counter variable position and 2 in the delta position. Finally, do some exciting arithmetic to generate the number 1003 and store it in our constant variable. Now we begin our main loop. The first thing we have to do is check whether we're done yet. Get the value of the loop counter, get the 1003 constant from memory, subtract, and compare against 0. If it's 0, go down, print out the sum, and terminate the program. If not, we continue the loop. Inside the loop, get the loop counter and square it. Now duplicate that value a few times, subtracting delta from it each time. At this point, we have 5 values on the stack. The bottom is our sum, and the next 4 are simply values we want to add to our sum. So add them together. That is, execute the add command 4 times. With the sum updated, get the delta value, add 2, and put it back. Finally, get the loop counter, likewise, add 2, and put it back. Then continue back to the beginning of the loop. And that's all there is to it. When the loop finally terminates, we'll have our answer on the bottom of the stack, we'll print it out, and we'll terminate. This also runs instantaneously using the online interpreter for Befunge 93 and solves Project Euler problem number 28 in Befunge. Tune in next time when we take a look at problem number 29 in Seriously. No, seriously, that's the name of the language. See you next time.